we go. Okay, great. Hi, everybody. My name is Bruce Momjian. I am one of the Postgres core team members. Been with Postgres for 27 years now. Yeah, 27 years last month. So this is one of 60 presentations on my website. You can actually see the other 59 presentations right here. There's over 100 videos and over 600 blog entries. So if you're curious or you want to see this presentation again, that's where you would go. This presentation is basically my understanding of the intersection between AI and databases, specifically with a Postgres focus. Obviously, AI is very popular. We've had some very interesting AI talks in this conference. I'll mention OtterTune, which I was at the talk yesterday, and I'll mention Tatiana's talk to this morning as well, where she looked at the OpenAI use of Postgres to write queries. So I'll mention that as we go forward. But what I'm going to start with is a very broad understanding of what artificial intelligence is, a little background of where it came from. And section 2 is probably, I think, the best introduction for machine learning and deep learning. That's a subset of AI, but it's the kind of AI that you typically see with cell phone apps and ChatGPT and image recognition. All those are basically machine learning and deep learning type of artificial intelligence. There are other types of artificial intelligence, but that's the kind that's become very popular in the recent years. Section 3, we're going to actually show some Postgres queries and show you how we use Postgres to actually do AI, a very crude example, but you'll understand it. And then to finish it off, we're going to basically go very specific. We'll talk about software and hardware, AI solutions and sort of how they work. We'll talk about some tasks, particularly that AI is good at. And then finally, we'll sort of bring the intersection together and look at how is artificial intelligence and databases, where does that really work and where is the value particularly to databases of AI. So really to start about what is artificial intelligence, this is a quote actually from this Wikipedia article down here, but effectively I think the key word is that artificial intelligence are machines that mimic cognitive functions. Not necessarily are they cognitive functions or not. It's not really clear if that's true, but they certainly mimic that. And they mimic functions that we associate with the human mind, such as learning and problem solving. Artificial intelligence, I've been around long enough to remember, artificial intelligence is this thing that's always 30 years away. We've actually made quite a bit of advancement since then, but again, it is a very fast evolving field. This is sort of my chance at, I don't get a whole chance a lot of times to talk about philosophical issues, but there is sort of a philosophical issue around what artificial intelligence is and what it says about our intelligence and whether our intelligence is basically a similar process to artificial intelligence or whether it's completely something different. So, if you're in the camp that would say that artificial intelligence is effectively just an artificial intelligence compared to our intelligence, which you can say you believe is the same but just naturally developed, you start to realize that free will or the concept of even the words that come out of our mouth or decisions we make are really not our own. We don't really have free will because effectively, if intelligence can be made artificially, then effectively we're just artificial themselves, and the concept of meaning and free will kind of start to get weird. So anyway, there's an article down there by The Atlantic which really opens up that issue, and if you're curious about it, I recommend you take a look at that issue article. The history of AI is really kind of weird. Pre-computer, there was a concept of AI, but it was more of a physical, if a physical device looked like a person, it was kind of artificially human, if you think about that. But then robotics became sort of what we consider AI. You think of machines that are doing processes that humans used to do. That starts to appear to be artificially intelligent. The Turing test, obviously from, I believe, the 50s and 40s was kind of a benchmark of how you determine if something is an AI thing. In the 1980s, expert systems were a huge area of AI. My boss, Mark Linster, actually got a doctorate at that time in expert systems. But unfortunately, expert systems didn't really take off, and we have a period called AI winter. I'm not sure how many have heard that term, but from the 90s up until about 10 years ago, you had a sense that AI just really wasn't going anywhere. People were trying stuff, but now, it's kind of resurfaced. ChatGPT, everyone's excited about. A lot of the things your phone does would be considered artificial intelligence. But also it has the sort of aura of being always 10 years away, like fusion energy is always 10 years away. When I was a kid, fusion energy was 10 or 30 years away, and it's still 10 or 30 years away, right? So, what does that say? I don't know. This is sort of a section where I just kind of open up that concept because I think it is interesting and I think that it is relevant to what we're talking about. This, I think, is a great quote from somebody from Microsoft. I have two quotes from this person, but it just really encapsulates. I'm going to read it in case you can't see it. In a certain sense, I think that artificial intelligence is a bad name for what it is we're doing here. As soon as you utter the words artificial intelligence to an intelligent human being, they start making associations about their own intelligence, about what's easy and what's hard, and they superimpose those expectations onto these software systems. So when Tatiana was talking today about OpenAI, I think that quote kind of brings in that concept. And the more that they try and align artificial intelligence with human intelligence, in a way you make the problem harder because you overlay assumptions about the capabilities of the software that really don't exist. Second quote I think is really great, same gentleman. AI algorithms are just math, and one of math's functions is to simplify the world so our brains can tackle its otherwise dizzying complexity. The software we call AI is just another way we arrive at complicated mathematical functions that help us do just that. And I will actually talk specifically about that mathematical concept in the example I use in section 3. Again, Wall Street Journal article at the bottom if you're curious. Okay, any questions? I know it's probably not why you came, but I had to sort of bring you into that philosophical bend so you start to have a realistic understanding of what we're talking about. So let's talk about machine learning and deep learning. Again, from this diagram, it's pretty clear machine learning and deep learning are parts of artificial intelligence. There are other branches out there. Deep learning is a part of machine learning. Machine learning be obviously a part of artificial intelligence. If you're looking for a video that really covers this topic, this video link here at the bottom is a link to a 3-hour MIT lecture about artificial intelligence. This, I think, was the clearest example. He uses an example, I believe, of image recognition, which I think was really, really well done. So feel free to take a look at that if you really want to kind of go in deep. Going really specific, and again, we're going to start to see references to human biology, things like a neuron, which effectively is another probably bad name for something, but that's what we have to use in the literature. But effectively, what you're looking at is what we call a tensor, which is sort of a group of neurons. So think of a tensor as a brain, maybe. Neuron is each individual neuron in the brain. Here we have a tensor with 3 neurons in it. So there are 3 measurements that we can make about the input or about the question we want answered. And you can see in the middle section, there's the training stage. So we actually are looking at the neuron first in its initial phase, where it's completely empty. All of the neurons are empty. In the second phase, what we're doing is we're loading training data into the neurons and into the tensor, and in each neuron, that training data is setting the weights for various inputs. Okay. We actually, in Tatiana's talk this morning, there was some reference to training data. And training data is effectively what it makes at least machine learning work, because you're continually loading in data that's going to help you predict or help you behave in the way that we want our machine learning to behave. And then finally, once we've gone through the training, we can then go into production. And at that point, you can see that the various neurons have different values, different heights here in blue. And we're basically going to load requests in, and then we're going to get results out. And that's going to be effectively our trained machine learning process. And this is where we're going to get results. Now, this may seem very abstract to you, but in the third section, we're literally going to show you the neurons, which are effectively SQL tables and functions and SQL functions and so forth. So we're going to put some specifics on this. But right now, we're still talking in the abstract. There are three types of machine learning. Again, the URLs here at the bottom are meant to give you further research. So if you want to dig into these type of things. Unsupervised machine learning is one of the rare methods of machine learning. In this case, as you can see from the second stage right here, we basically have training data that doesn't really have any results to it. It's just sort of random, like not only say randomly put in, but you're putting the training data in, but you're not really giving a desired output for your training data. Okay, and this is not used a whole lot. There's only a couple examples I found of this. But again, this is the simplest case where the training is just going in and the system's just kind of measuring without really having any target. The much more common and most common, I would say, machine learning is supervised machine learning. In this case, you're putting training data in with results. So for example, let's suppose you're trying to distinguish dogs and cats in an image. So you send in a whole bunch of pictures of dogs, and the result is dog for every one of the dog pictures. And then you send a whole bunch of pictures of cats, and the result is cat. And then once you've done that thousands of times, you basically get to your production, which is the bottom. You send a picture in, and you hope that it properly identifies dog or cat for you. Okay. Now it could be something else. It could be words. It could be sentences. It could be how tall is the Empire State Building. I mean, this is, there's no limit to how much it can be done here. And again, people are even more recently are playing with ChatGPT to see exactly what's possible in the outputs here. A more sophisticated example of machine learning is something called reinforcement learning. Reinforcement machine learning. In this case, initial state's the same. The middle state, the training state's the same, because as you can see, we're feeding training data in with results. Okay. But what's different about the last section is we're sending requests in, we're getting results, but we're also feeding results back into the neurons. So here, not only are we learning at the training phase, but we're making adjustments during production to improve the results, basically. Okay? There's a whole section of AI, machine learning, really designed around how do you feed these results back? How do you do it in a way that doesn't overwhelm the system? You want your results to have a certain weight, but not too much weight, right? Because you can't just blow away all the training data with one incorrect representation. So for example, let's suppose We're using this to predict fraudulent credit card charges. I'll show you an example later in my talk about that. And you feed in a number of valid credit card charges, the location, all these others, the amount, the vendor, and then you feed in a bunch of fraudulent ones, right? And then you go to production and you send in, results, and send in data and you get results out. But what happens when it guesses incorrectly? You want to get that information back into the model so that the system becomes better as threats evolve, but you don't want to do it too much or you end up kind of distorting your model. Again, very, very interesting field here. Deep learning is, again, a subsection of machine learning. This is a case where instead of having one set of tensors, with initial and training and production, you're now connecting them together. So the output of the first tensor feeds into the second tensor feeds into the third tensor, and so forth. You see this a lot for things like image recognition. So one tensor is going to study the colors in the image. Another one's going to study the shapes. Another one's going to study maybe look for certain indicators like a tail or what, I don't know all the details. But if you think of, for example, the way voice recognition works, someone's going to look at the pitch of what the person's saying, and then the speed at which you're saying it, and then what letters came before it. So you can see how you would layer these tensors together to do more complicated tasks. And most production tasks are going to probably need to do deep learning because you can't necessarily have one set of measurements to do everything. You've got to kind of feed them in. So it's going to be pitch, volume, what word came before it, what sound came before it. There's all these things that you can do, and they kind of all basically add on together. Any questions? Oh, okay, good. All right, so let's be very specific. I'm going to create a simple supervised machine learning system in Postgres in this section. Okay, we're going to have neurons, we're going to have tensors, we're going to have training data, and then we're going to actually go into production and we're going to get some results. Okay, so this very simplistic machine learning example I'm going to use is predicting if a number contains a non-leading zero. Right? Now, I realize we could do this very easily with mathematics, right? You could very easily just spin through the digits and determine if there's a zero. But we're not going to do that because it would just kill the whole thing, right? What we're going to do is we're going to look at specific things that we can measure, and we're going to try and predict based on those measurements, is there the probability that there's not a leading zero. We're never going to be sure, but we're going to go by probabilities here. So as you can see, the first bullet here, that one is true, but the second bullet is false. So you get the idea. Is there a non-leading zero in the number? Yes or no? Okay. So we're going to do this in Perl. One of the reasons I did this in Perl is I can get the Perl scripts on one screen because Perl is very concise. It's very easy to use. And in fact, all of the SQL I'm going to use in this talk is actually at this URL here at the bottom. So if you actually want to run this yourself and see what results you get, just download that SQL file and run it through PSQL, and the whole thing will just fly by on your screen. But I'm loading in a PL Perl extension. And then I'm creating, here's our first reference to the previous site. We're going to create a tensor. All right? Function create tensor, generate tensor. And it looks like here we have, this is a scalar. We're going to pull a value here for a tensor. And it looks like our tensor has 11, it's an array, so I actually have 11 neurons. Well, it actually works with our terminology here, right? I'm going to actually have 1 to 10, and the 1 to 10 is just going to count. It's going to have a different neuron for how many digits are in the number. So the more digits in the number, the more likely there's a 0 there. In general. Now, this is not perfect, but you can imagine the longer the digit is, the less likely there wouldn't be a 0 somewhere, right? And then I'm also going to have another neuron which says, is this number divisible by 10? Which I'm deciding I can do. I can look at the last digit easy, okay? And then, so I'm gonna basically create this array, and then I'm going to basically run through the array and map it to true and false based on the input I've gotten, okay? And then I'm going to encode it and load it into a Boolean array, basically, and return it. So that's kind of what's going on. I'm going to take a value, I'm going to run it through my tensor, and then return a result. Okay. So now we're going to look at our training stage. Remember the second stage of artificial intelligence here. Here's my training set. So I'm going to just create a table called training set. I'm going to load 10,000 numbers into that with random values. Okay, it's basically a random number of digits. So, from 1 to 8 digits, and I'm going to make those random, and then I'm going to insert those into the training set. So this is a common table expression, but it makes it kind of clear exactly what's going on. I generate 10,000 numbers, and then I load them into my my training data. Okay, all right, great. So this is what it looks like. These are my tensors, effectively, with 11 neurons each. So, for example, this number right here is it at least this many digits? And in fact, it's actually at least that many digits all the way out. Is it divisible by 0? No. This one, the same thing. Here's the 72. Notice I only have 2 trues, and the rest of them are false. And then I have a false here. This one's mostly true. This one's mostly false. So again, depending on how many digits I have more trues or more falses based on what's going on there. Okay. I also have another function, and again, we're getting into some details of artificial intelligence using machine learning. We have something called generate weight, which effectively takes all of the neurons and balances them so they all total to 100%. Because, as you can imagine, you have different probabilities, and you want them all to be basically balanced out. So we have a generate weight function here that basically runs through the neurons, and then it basically balances them all out so that if something's 10% and something's 20%, something's 5%, when you add up all the neurons together, you get to 100. That's effectively what's going on here. Again, compute percentage and balance the weight. So that's what's kind of going on there. That's a big function, but there's no other way to do it. We'll get lazy. Okay. Something called a tensor mask. This masks out the values we don't care about. So again, depending on which neuron we're looking at, we can mask out the ones we don't care about effectively. We only are going to use the probabilities of the ones we picked and not the other ones. Okay. Sum the weight. So this is used to run across all the tensors and generate a sum of the weights, and we just output that sum there. Softmax, again, it normalizes the values so that the probabilities total 1. So what we now do is we create our tensor rate. We have a tensor values for the value true, for cases where it's true, and we basically select from our training data. So we run through this training data, and we generate the weights, and we load them into this table. We do the same thing for our training data for false. So this one would be the true training data. This is the false training data. And what we end up here is the weights of the various neurons in our tensor. And I believe if you add all these up, I think they become, I think they get to 100 or something like that. I'm trying to remember how I did this. And same thing down here. This is our false. And we basically have balanced these out. So how do we actually use this now that we've done the training? Here's the number 100, and we basically run 100 into our generated tensor, and then we compare it with the weights. We go with the mask. We sum the weights together. We run softmask, and we get this output. What it's telling us inaccurately is there's a 22% chance there's a 0 in there. Not great, okay? And the reason it's so poor is because there's only 3 digits. So it's kind of thinking, this is probably not going to be good. Now, when I do 101, notice this is actually accurate. This is actually worse. It's telling me there's an 11% chance there's a 0 in there. Okay. So again, the system doesn't know what the tensors do. We know that divisible by 0 should automatically mean there's a 0 in the number. Right? Divisible by 10 means there's got to be a 0 in there, right? But it doesn't know that. It just went by the training data. But you do notice it does do it from 22% to 11% as soon as we lose that last tensor, which is considered to be fairly significant indicator of what we're doing. Here we have a number with no zeros, and it accurately has a 68% chance that there's no 0 in there. That works pretty well, okay? So what we can do is we can run 1,000 numbers, 1,000 random numbers into our system here called test set. We then run our tensors with the mask and the weight, and then we generate that, and then we do an analysis, and we figure out how close the number was to accurate, and we get effectively this down here, and it says that, actually right here. So it's basically telling us that the system was about 72% accurate, I mean, roughly. So not great, but when you generate enough numbers, it starts to get kind of closer. Obviously, no one would use this in production, but you can see how this would be used in a more practical case with a lot more data, with a lot more test data, okay, and a lot more smarts in terms of choosing the tensors and so forth. Any questions? Okay, great. Okay, let's look at the hardware-software angle here. Postgres does support artificial intelligence in 2 different places. You can use artificial intelligence on the client side. So something like TensorFlow or MATLAB are certainly Scikit, and here's some URLs about somebody blogging about that. But you can also do AI on the server side. So instead of having to drag all the data to the client and do the analysis and bring it back, you're actually storing the data in the server, and you're doing all the AI in the server. It is very confusing that we have a MATLAB and a MATLib. I've often thought, I forgot the name. And in fact, there's 2 of them, and they sound almost the same. What's also interesting is you can use Scikit in both the client side and the server side, which I think is really kind of fantastic. As you can imagine, when you start to get into machine learning, there's a huge number of computations involved. So if you've heard people talk about the use of, for example, GPUs to do artificial intelligence, and you wondered why are GPUs so important, it's because this computational complexity, if you have, let's say, 1 million neurons, and you go to compare against 1 million neurons, you're looking at 1 trillion comparisons there, right? So that's really that's really very computation expensive. So deep learning is going to use a lot of this kind of case as they go through the repetitive calculations and so forth. And GPUs are designed to do that, very efficiently. Looking a little, maybe going a little more to practical, what types of tasks is artificial intelligence good for? When I was a kid, they had these computer, chess games, and it was kind of amazing how good it was. But chess is obviously a very limited set of options, so it's a little easier. You might remember Deep Blue beating somebody at Jeopardy. That was sort of a big milestone, I think, for artificial intelligence, although ultimately Deep Blue practically really wasn't very much of a success. They they kind of won Jeopardy, and IBM kind of tried to get it adopted, and a lot of people tried it, but in most cases, the results were disappointing. And ultimately, IBM sold off Deep Blue. So sort of a sad ending, but you can't. It's illustrative of some of the challenges of actually getting AI to be realistic. Voice recognition, I think, is a great example. We use that on our phone pretty regularly. It isn't always right, but it's pretty close. And again, it learns from you over time. Search, use of AI for search, we've seen that done. Recommendation engines using AI, we've seen that. Image detection, I talked about that. Weather forecasting, that's been in AI for years, where you look at patterns of weather and you feed in a huge amount of weather data from previous outcomes. Is it going to rain today, right? You just feed all this in, and then you feed in today's forecast, you get a result out. So that's actually been around for a long time. I think a great example, frankly, and I have a URL here from a bank explaining it, is fraud detection for credit cards. When you're trying to do fraud detection for credit cards, you start to wonder, well, what do my neurons look like, right? In my tensor, what things am I going to be measuring to detect fraud? Now, you can detect millions of different things, but you have to sort of think, well, what would be, what would be a reasonable thing to do? So what they used to do with expert systems, and I can kind of bring you from the 80s to today. So with expert systems, what they would do is they would sit down with somebody in the industry who had spent a huge amount of time in fraud detection. And they'd say, what things do you look for in fraud detection? You say, well, we look at this, we look at that, whatever. And they would ask the person, how important is this aspect for fraud detection? And they would end up basically coding the knowledge of the person by talking to them into a program, and they would use that program for fraud detection. Okay, makes sense. But the problem is people are pretty poor at estimating the importance of various parameters when they make a decision, frankly. And the system was not learning. It would just do what that person had learned from previous, and any new frauds, you'd have to ask them again, right? Or recode it or something. So what they, in a way, in my mind, what effectively has happened is you've taken the questions you would ask for expert systems if somebody's looking for fraud detection. You may use the same measurements or the same neurons, if we're going to use that term. But instead of asking the person for how important are all these things for fraud, you feed in millions of valid, can't have that happen, can we? You feed in millions of valid transactions, and you tell the system, here's valid ones. And then you feed in millions of fraudulent transactions. You tell them they're fraudulent. And what happens is all those neurons that you normally would have hard-coded from the interview with the expert are now being set by the data that you put into the system. So you might find out, for example, that you might get this list, how high was the charge? What type of charge was it? Chip, swipe. How far was the vendor from the billing address? When was how far was the last charge from this person? What the country, previous charges, fraudulent charges by that vendor, right? And you start to, you send a bunch of data in, and it's going to come out and it's going to say, okay, you choose the attributes, right, which we talked about, and you create the neurons for those, and then you create a training data set. And number 4, you feed all that data in, okay? And all the neurons, basically based on how predictive that was, get set, right? And then you start feeding real data in, and you get much more accurate results than you would have if you tried to code these neurons manually, right? And then finally, we talked about the concept of feedback, right? You feed correct and incorrect results back in to adjust for future fraudulent cases. Okay, and I think it's a good example of actually taking this AI and applying it to something that kind of makes sense, you can understand how setting the neurons for valid and invalid charges would kind of work in this case. Okay. And finally, actually, any questions about this? Okay, great. So to wrap it up, this is our last section. Why use a database? What do you this is Postgres in the AI landscape, right? Why would you use a database in this case? So let's think historically. I mean, typically people thought of a database as just a place to put financial data, a place to put records, telephone calls, sort of a place to record things, right? But as things have evolved, there's been additional needs. So one of the early needs back in the 90s, 2000s was data analysis. So that was added to relational systems. Then people wanted analysis of text documents or analysis of document text. And then full text search was added to Postgres, right? Then people wanted GIS analysis, and that was added to Postgres, right? And then people wanted JSON so that they could interact better with web traffic. That was added to Postgres, right? Key values, NoSQL type of data. So the reason I'm saying that Postgres as a database is kind of inevitable in a way is that if you look historically, every new technology kind of started outside of the database, right? Whether it's GIS or full text search or JSON or analytics, right? And over time, as the technology evolved, it started to move into the database. This is actually, Peter Zaitsev on Tuesday talked about data gravity, where data starts to gravitate toward other data to allow for the interactions to be studied. And I think you're going to see this going forward. I don't know what that looks like. I think we're in the early stages, but I would imagine that there is a potential opportunity here. So, and there's a couple of signs, I think. First, machine learning requires a lot of data. We talked about training data. We talked about the need for that training process. If you're going to feed data, why would you not feed it in from the place that has the most of your data, right? If you're feeding in fraudulent transactions, you would probably find most of them already in your database, as well as valid transactions. So there's a sense the data is already there to create the AI models. Most of the data is already in your database, and then again, why not do the data where the analysis where the data already is? So advantages are effectively you have already previous activity that you can use as training data to load in. Allowing seamless access to all of your current data is helpful. Having a separate data store and keeping it synchronized is always a very difficult process. You can even use things like artificial intelligence to take immediate action. For example, you're about to commit a transaction, you can actually run an AI model and figure out what is the likelihood this is an invalid transaction, right? You can do that right in the database if you want. Again, by doing it in the database, you have concurrency, backup, consistent transactions. Postgres already has a lot of the tooling you may need, like GIS to compute distances to vendors, full text search for analysis of the type of transaction it is, complex data types, complex indexing, and Postgres can even do GPU type of analysis in the database. So again, I've really talked about how we can have user applications use AI. There are other opportunities. So Ottertune from yesterday, the man in the big brown outfit with the red top, he talked about using AI not for user applications, but in fact to create more performant databases by adjusting the tuning using AI. Again, things like optimizer, indexes, database settings. He particularly talked about database settings, but mentioned that his product can do most of these as well. And also alerting. So things like alerting for anomalous activity. You could also do that with an AI system, and again, report to your administrators. So that is actually all I have about AI. This image is actually from Phoenix. There's 2 or 3 reasons I chose that image, but you can guess why. But I'll be glad to take any questions. Looks like we got about a couple minutes to go. Any questions?
Now you have me curious about the picture.
What's this?
Now you have me curious about the picture.
Yeah, so it is a real picture. It is not a fake picture. So the 2 reasons I picked were, one, that, I don't know, okay, we'll do it again. I think it's probably me. I'm probably grabbing it somehow. One is that the squares actually look like the neurons in the system. And the second thing is that the squares are actually creating an image of a real thing, right? So it's effectively, when you're looking at the building, you are not looking at clouds. You're really looking at neuron reflections of clouds, right? So yeah, I was just kind of struck by, it's creating, it looks like you're seeing through the building, but in fact, you're actually seeing reflections that look real. It looks like real intelligence. It looks like real cloud, but it's not. It's really just a reflection. So those are probably the 2 things that kind of struck me about this. And usually when I write my presentations, it can take me 20 minutes just to pick one picture. It depends. So because people see this over and over again, and you want to give something that's got a depth to it. So this is one of them. Great. Well, I don't see any questions. So you have anything? You're good? Okay. Thank you very much. I hope you have a great rest of the conference.